Okay, can you see my point here? Is there any questions?
Yes, sir.
So yeah, so what the parallel transport that we enjoy in flat space is no longer a privilege in curve space. Yeah, in other words, not all curves, not all path of vector transport is the same as parallel transport. Okay, it's not the same as parallel transport. So if that is the case, then the question is, can we determine which curve is the parallel transport? If that is the case, can we determine which curve is the parallel transport if different curves or different paths lead to different direction of vector? Well, the answer is yes. We can always find the correct path that leads to parallel transport. Okay, and how to do that? How to do that? Well, to do that, we know that in flat space, yeah. So, so in flat space, we know that in flat space, if we have a function given a curve x mu, a function of lambda, if you want to bring a vector, so I have a vector, let's say that the vector is v mu. So I have a vector, the vector is called v mu, and the path or the curve where the vector is transported is called the x mu or x alpha, let's say. I'm taking it x alpha function of lambda. Now, the requirement that the v mu should be constant, constant in magnitude and constant in direction along this curve is equivalent to saying that I want to have that the dv mu d lambda is equal to 0, right? If this is not the case, then v mu will not be constant, and by not being constant, I mean it's either not being constant the magnitude or its direction. Okay, it's either one or both. It can be both. Now, to be constant, it means that the v mu d lambda should be 0. Okay. So using this from here, using the what we call the chain rule, yeah, I can do it like this: dx alpha d lambda, and this is well, partial v mu partial x alpha, this is equal to 0. Okay, so this is the requirement that vector v mu is parallel along the curve x alpha. This is the requirement that it be parallel. Now, in curve space, this requirement is insufficient. Why? We know that in curve space, this object is not a tensor, right? This is a tensor because this is the derivative of a vector with a scalar. Okay, this is a derivative of the dx alpha d lambda is a derivative of a vector with scalar. So the result is a vector. But this is in curve space. This is not a vector or not a tensor. So in order to have the same equation but compatible with the curve space, we need to modify it a little bit. So in curve space, the the equation, yeah, is as follow. Instead of partial v mu partial x alpha, we have just the covariant derivative or del alpha of v mu. So this is the appropriate equation in curve space. Now, if I am extending this, we know what this is, right? So we know that if I work this out, del alpha works on v mu is just partial alpha of v mu plus gamma mu alpha beta, let's say, and this is v beta, and this is equal to 0. Okay. So this is the equation. Okay, if I'm bringing it back, if I'm bringing this back inside, I have dx alpha d lambda. This is the partial v mu partial x alpha plus gamma mu alpha beta dx alpha d lambda of v beta is equal to 0. Okay, or this is just dv mu d lambda plus okay. Now okay, so this is the result. The question is, well, I mean, this is the equation that guarantees that our vector. So vector, if this is the equation that vector v mu must satisfy in order to guarantee that it goes parallel transport along a curve x alpha. Okay. Now, if it happens that if v mu happens to be the tangent vector to a path x mu, yeah, v mu happens to be the tangent vector. Tangent vector means a vector that is tangent to a point, or a vector yang menyinggung titik itu ya, menyinggung manifold di titik tersebut. The tangent vector to x mu, yeah, then we have the relation that v mu is simply dx mu d lambda, right? Because this is the requirement for the tangent vector. So if this is the case, then what happens here? We have the equation that this is just x mu double dot plus gamma mu alpha beta. We have here a x alpha dot, and here we have x beta dot. This is equal to 0. But what is this? You see that this is nothing but geodesic equation, right? This is nothing but the geodesic equation. So what does that tell us? It tells us that if you have a tangent vector to a curve and you want to transport it along that curve, then that can happen if the curve you pick is the geodesic curve. If the curve you pick is the geodesic curve, then you can successfully do the parallel transport of your tangent vector along that curve. Okay. In other words, the path of parallel transport of a vector along any arbitrary curve is the geodesic curve that you can draw from initial point to the final point. Okay, any question about this? Another way of saying this is that I can use this as a definition of a geodesic. Yeah. So this is a new definition, or a new way of looking at the geodesic. So geodesic can be defined as a curve along which, the tangent vector is, we call it autoparallel. Autoparallel means that it is always parallel to its original form. Is autoparallel. This is what we call the geodesic. Okay. Any question? Okay. Well, at this point, I think we can get more intuition about curvature. Remember that we are going into differential geometry, even though it's just brief, in order to understand gravity, right? Because as my earlier conclusion, gravity can be perceived as the geometry, as a phenomena, as a geometrical phenomena, right? Gravity is no longer a force, but gravity is the curvature, geometrical curvature of space, or space-time to be more appropriate. Now, then we ask ourselves, what is curvature? Okay, and that's why we go into this geodesic and also the parallel transport. Now, I think we can start answering what curvature is. Okay, now I'm gonna talk about curvature. Curvature. What is curvature? Can you define curvature? Well, our definition of curvature, if you observe, it's limited to our daily perception, daily observation. For example, you can intuitively say that your blackboard or your whiteboard or your piece of paper is curved. Sorry, is flat. I'm saying, okay, but your surface of basketball, your the surface of your football, yeah, soccer ball is curved. Okay, and that's correct. Yeah, those objects are two-dimensional objects. Yeah, paper, a piece of paper. Well, a piece of paper is three-dimensional object, but effectively it's two-dimensional because the thickness of the paper is very much uh, less compared to the length or the width of the paper. So we can regard paper as just two-dimensional object. Your blackboard or your whiteboard is also two-dimensional object. Your computer screen is two-dimensional object. Okay, and the surface of a sphere is also two-dimensional object. Okay, and we can determine whether a two-dimensional object is flat or curved since we are three-dimensional creature. Okay, we are three-dimensional creature. Now, in that sense, we determine curvature by looking from the higher dimension. Yeah, we determine the curvature of lower dimensional object by looking at higher dimensional by looking at higher dimension from higher dimension. Okay, we are three-dimensional creature. That's why we can tell whether a two-dimensional object is curved or flat. But can we tell whether our three-dimensional space is curved or flat? It's kind of like difficult question, right? Because in order to answer that, then we have to go higher from three dimensions. We have to look from 4 dimensions. But we are three-dimensional creature. We cannot perceive the 4 dimensions easily. Yeah. So it seems that we cannot tell whether our our three-dimensional world is curved or flat. Okay. Bisa dipahami statement saya? Jadi intinya adalah selama ini persepsi kita mengatakan kalau kelengkungan itu bisa ditentukan karena kita adalah objek yang higher dimension, kita menentukan kelengkungan dari objek yang lower dimension, kayak two-dimensional or one-dimensional objects. Ya. Tapi kalau kita disuruh menentukan kelengkungan dari three-dimensional space or even four-dimensional or higher dimensional spaces, kita nggak bisa, ya. Karena berarti kita harus melihat space itu dari even higher dimension than them, ya. Nah, jadi itu problemnya. Ya. We have a problem with defining curvature. Ya. How can we define whether a manifold is curved or flat? That's a bit of problem. Saya ambil contoh gini. Saya ambil contoh, misalnya, I'm gonna tell this in English ya, but I'm gonna tell this in Indonesia first. Misalnya Anda adalah seekor kutu, ya. Katakanlah kutu itu adalah binatang 2 dimensi. Katakanlah dia nggak bisa mempersepsi dimensi ketiga. Dia hanya bisa bergerak maju, mundur, kanan, kiri. Ya, tapi nggak bisa bergerak atas bawah. Gitu kan. Kalau kutu itu berada pada permukaan bola, bagaimana dia bisa menentukan bahwa permukaan bola itu melengkung dan tidak datar? Dia nggak bisa melihat dari atas. Ya. Dia tidak bisa bergerak naik turun atas bawah. How can he determine? Dia nggak punya cara ya. Tapi minimal dia tahu kalau saya bergerak ke satu arah saja, keep going, maka saya akan kembali ke titik awal. Ya. Buat dia itu sesuatu yang aneh. Ya. Karena dia nggak punya persepsi bahwa dunianya itu adalah curve, bukan flat. Gitu. Buat seekor kutu, ketika dia tetap berjalan di satu arah dan dia kembali ke titik yang sama, itu sesuatu yang aneh, sesuatu yang dia nggak bisa jelaskan. Tapi buat kita itu sesuatu yang simple ya, ya karena Anda bergerak melingkar, jadi Anda akan kembali ke titik awal. Okay, I was saying that imagine you were a bug, a two-dimensional bug, yeah, living on a sphere, living on the surface of a basketball. Okay, as a two-dimensional bug, you can perceive forward, backward, right or left, but you cannot perceive up and down. You cannot go up and down. Okay, you can just move two-dimensional. So how can you determine whether the space you live in is curved or flat? Right? It's kind of difficult. And you might encounter a weird fact that if you as a bug, if you move along any direction, you can pick any direction, and then you keep going along that direction, eventually you will come to the place where you left, right? You cannot understand that as a bug. You wouldn't understand that because you cannot perceive the third dimension. As a human, a three-dimensional creature, we can easily understand that. But as a bug, as a two-dimensional object, we cannot understand that. So the same thing happens. We cannot perceive whether our space, a three-dimensional space, or even four-dimensional space-time is flat or curved, right? It's just beyond our imagination. We cannot comprehend that. But the question is there any way, is there any mathematical way that we can determine that any space is flat or curved without having to refer to external or higher dimensional external space, external reference? Can we determine whether our three-dimensional space is flat or curved without having to go or having to perceive it from four dimensions? Well, fortunately, the answer is yes, we can. Yeah. In mathematics, there is a way to determine that. In geometry, actually, in differential geometry, yes. And how do we do that? Well, we can learn from our previous example here. You see here that actually, what does the path 1, 2, 3, 1 represent? This is a closed path, yeah. A contour start from 1, go to 2, go to 3, and goes back to 1. So this is a closed path, a closed contour. Now, if you have a closed contour on a manifold, and then you see that if you do the parallel transport along this closed contour, okay, but then the result, your vector is no longer parallel, then there is an indication that your manifold is not flat. You see, if I'm bring this vector along 2, it goes like this. I'm bringing it along 3, it goes like this. And if I'm bringing here back to 1, what do I get? I will get like this. I will get like this. So the vector is no longer parallel. It makes a angle, right, with the original vector. This it doesn't happen when you are in. It doesn't happen if you are here in flat space. For example, if you are drawing something in flat space like this is flat space, flat two-dimensional space. If you are having a different loop or contour, close contour, you can always bring your vector transport it along this contour and go back with the parallel condition. Okay, but that's not the case if the manifold is not flat. So here you have a notion to determine the curvature of a manifold. So yeah, so the first question is, what is curvature? The second question is, how do we determine curvature? how do we determine the curvature? Well, the answer of the second question is by doing parallel transport along a closed loop, any closed loop. Okay. If, for example, you have a as I said before, yeah, that your vector is no longer parallel, then you can convince yourself that the manifold you are working with is curved. So the answer of question 2 is we can simply doing parallel transport, doing parallel transport of a vector around some closed loop, yeah, around some closed loop or a contour, and see whether the vector fails or not to remain parallel, yeah. Whether it fails or not to remain parallel. If it fails, then your manifold is not flat. If it if it doesn't fail, you cannot simply conclude that your manifold is flat. No, because you have to prove that for all contour that you draw, for all closed loops that you draw, the vector keeps parallel. So in that sense, proving the manifold is flat is much harder than proving the manifold is curved. Because to prove that the manifold is curved, you just pick, if you can prove that at least there is one closed loop that fails you to become parallel, it's sufficient to prove that the manifold is curved. But to prove that the manifold is flat, you have to show that all closed loops that you can draw gives you parallel transport. And that's kind of hard. Okay. So here we have the question, the answer for question 1. What is curvature? Here we can define curvature as, so what we call curvature is basically the failure of what? The failure of a tangent vector or a vector to remain parallel. So curvature is defined in terms of failure, yeah, to remain parallel with respect, okay, with respect to its original direction when parallel transported along a closed loop. Original direction when parallel transported or when transported, actually, yeah, just when transported along a closed loop. Now this is important, yeah. Closed loop. If it's not closed loop, then it cannot guarantee that the result is parallel or not. Yeah. Along a closed loop or a contour. Okay, I think I can stop here. Yeah, we can continue after the exam. Any question? So here we define the notion of curvature. Later I'm gonna show you how we can calculate curvature quantitatively, mathematically. This is just qualitative definition. Yeah. Next, we are going to interpret this qualitative definition into a quantitative analysis or quantitative mathematical quantities, yeah, so that we can always calculate the curvature of any arbitrary space that we have. Okay? So if you are given an arbitrary space, you can always calculate its curvature. We are going to study it later, yeah, maybe next Friday, because on Monday you're gonna have exam, and as I said, the exam is gonna be take home. Yeah, you can check your AMAS. It's gonna be on AMAS on Monday. Okay, and the due date is on Friday. Okay. Question?
Sir, is there any creation lower than 3 dimension or higher than 3 dimension that can understand maybe higher or lower dimension? We can understand lower dimension like 1 and 2, but not 4, 5 or more than that. Is there any creation
Observer, you mean observer like creature?
Yes.
I don't know. I don't know. So far, science haven't found it.
And about this definition of curvature, the failure of a tangent vector and normal vector. You said tangent vector, but you wrote vector. Is there both of them will fail to be parallel?
Yes, both of them will fail.
Any vector will not be able to be
Yeah,
parallel.
I mean, if you pick any random arbitrary vector and then you try to do the parallel transport along some closed loop, and if it happens to be if it happens to fail, then you have a proof that your manifold is curved. But the reverse is not true. Yeah. For example, like this, I have this sphere. Sphere is curved, right? But I can find a closed loop where this vector keeps parallel. Okay, what's the closed loop that I was talking about? The equator. This is a closed loop, right? If I'm bringing this vector along this equator, when it goes back to this point, the vector stays. It's parallel. Okay, because that's the definition of parallel transport. Yeah, the definition of the curve, the autoparallel curve. Yeah. So this shows that in curve space we can have a closed loop where the parallel transport is successful. That doesn't mean that this manifold is flat. No, because we know that the manifold is curved. So that's why I was saying, in order to prove that a manifold is flat, you have to show that all closed loops, not only one, you have to check that all possible closed loops fail to do parallel transport. Okay, so in that sense, proving the manifold is flat is much harder than proving the manifold is curved.
Yes.
Okay. But later, when we devise a mathematical object or mathematical tensor to calculate curvature, it becomes easy because we can just plug in that object. We can calculate it mathematically, and if the result is 0, then the manifold is flat. If the result is non-zero, the manifold is not flat, just like that. But I'm gonna talk about it later. Any other question?
Thank you, sir.
Okay, if there's no question, I can stop here. Yeah.